I hope everyone's having a great evening. I am Mr. Ish. Thank you for joining me for this video. I want to show you how you can go around developing template formulas for volume cross sections, where the cross sections will always generate some form of a disk. We will be using a sphere as our model solid for this particular video. You know, a sphere is a solid which has a volume 4 over 3 pi r cube. You can start everything here with the unit circle formula and then solve for y, and you've developed your function square root r square minus x square. Graphically it looks like that. When you rotate this around the x-axis, this curve, you will generate a sphere. This curve is your r square minus x square within a radical. At any point from the x-axis looking up, you're always developing a radius, and that radius is exactly that right here, this function. If you pluck out a cross section from here, it's a slice, not a disk, because it's a two-dimensional with a line over here having 0 to no width. Because a line has no width, it has a dimension of length but no width. Anyhow, this cross-sectional slice is circular. It has a pi r square. You send this right here through the area formula, pi r square, and you'll get this as your area of each slice, which when you integrate from a lower limit, you know, minus r to r, you will develop that volume minus r to r. You have the pi pushing out, you will have r square minus x square dx. This integrate all the way through, you get this 4 over 3 pi r cube. But that's not what this video is about, showing you how you derive this. I've done that in another video. What I want to show you is how can you use this entire representation to start generating volume formulas for cross-sectional disks, not slices but disks. And what is it would look like? Well, here's a sphere and I'm drawing an x and y axis in it. If I were to generate a lower limit here, upper limit here, and then look up across, up and down, and pluck this entire portion out, it would look something like this. And you know it's gonna have a certain three-dimensional attribute to it because it will be indeed a disk. That's a disk which has been plucked out of your sphere. And if it's a disk, it has a certain volume. If it has a volume, it must have a formula. How can we derive formula for such solids? Your basic point is to understand you're not looking at a complete integration from one end to the other. You're looking at a partial integration from A to B. By partial, I'm talking about partial domain. Rather than looking from minus r to r, you're looking here from A to B. When you integrate this by means of a rotational effect, you will develop a disk with a certain volume. And this is exactly what the integral will start with. You'll have a pi. You have here r square x minus x cube over 3. This will integrate from B and A. This here is exactly what will give you your formula. You have a pi r square into b minus a minus b cube minus a cube all over 3. What am I doing here? I'm putting the upper limit, lower limit in places of x, and their difference is always being done. You have a common denominator. You can develop pi 3r square b minus a minus b cube minus a cube all over 3 right here. You've seen this, how everything has come about. It's no different than a sphere volume integral, except you have a and b. By doing cross-sectional disks, you're using partial domains a to b rather than minus r to r. And everything here is with regards to sphere, as you already know. You can isolate over here and clean things out. You can isolate a pi over 3, pull it out, but you can isolate a b minus a also. And it'll go in here 3r square. B minus a is present here. Remember, a cube minus b cube or x cube minus y cube. It's a factoring formula you learned in algebra. It would be b minus a times b square plus ab plus a square. That's what's going to happen. And that's what's going to be left behind. B square plus ab plus a square. This right here is our formula that we want. It's a template for you which will give you a volume of a disk generated from a sphere given a certain radius, dimension, and limits a and b. Everything here is in play for you to see, and it's a good formula and it's right, and I'll show you why it's right. Imagine we will take a large slice. If I have here from minus r to r, where r is equal to 1, you know when I'm doing the formula over here with r equals 1, the volume will be 4 over 3 pi. R cube, 1 cube is meaningless, it's just 4 over 3 pi. Imagine my large slice is actually a large portion of the sphere. I'm going from 0 up to 1. Instead of going from minus 1 to 1, I'm going from 0 to 1, so I'm going to pluck out half of a sphere, which means my half of that sphere should have a volume 2 over 3 pi. If I can generate a 2 or 3 pi from here, I know my volume of this disk template is good. R is equal to 1, my A value is 0, my B value here is 1. Where you see R, put a 1, where you see A, put a 0, where you have B, put a 1. You have a pi over 3 times B minus A, which will just be pi over 3. You have a 3R square, which will just be 3, because R square is a 1 square, which is a 1, minus B square, 1, plus 0, plus 0. This is a 1, 3 minus 1 is a 2. You'll have a 2 pi over 3 as a volume of a disk, which in this case will happen to be a hemisphere, but going from 0 to 1. So there should be no doubt that this volume is wrong. It's indeed right. And this volume template for you specific to a sphere is this. So if you have a sphere and you want to determine the volume of a cross-sectional disk you will generate from that sphere, you need to know only a radius and what your limits will be. That's all what you need to do, and you'll be good. Here's my sphere. It has a certain radius, and I'm looking here from perhaps A here to B here. I can take this entire portion, pluck it out, and it would look like a pretty interesting disk. It would look something like this. The volume of this specific disk would have a numerical value derived from this formula that you see right over here. Pi over 3 times B minus A, large parentheses, 3R square minus circular parentheses, B square plus AB plus A square, close all your parentheses, and you're done. That's what I want to show you here in this video. A similar exercise can be done for whichever rotational solid you want to do. Here we're just looking at sphere. Thank you for watching and have a good day.